Gravitational force is one of the, we have a few of those lecture videos up. I should post a link in Canvas so that y'all can review them if you feel like it. Gravitational force is one of the fundamental interactions, and it's a little bit complicated. We figured out last time what the equation for gravitational force has to look like, and it looked like this. If we have some object that we'll call 1 that we've chosen as our system, and this is an object that has mass, and mostly when we're talking about gravitational interactions, the gravitational force actually isn't a very powerful force, a very strong force. So it takes a big mass to have a big effect. So we're often talking about things like planets and spacecraft and stars and whatnot. We talk about these things even though a proton and an electron do exert gravitational forces on each other because they have masses, albeit very small ones. And so if we have something that we're interested in, this is our system, we want to find the force on this system due to some object in the surroundings. Then the gravitational force on 1/2 was equal to a minus, there's a constant, big G, whose value we'll tell you in just a minute, times the mass of object 1, mass of object 2, over the magnitude of r squared, r hat, where what is r? R is a relative position vector. It starts at the object in the surroundings that's causing the interaction, and it goes to our system. So and it has units of meters because it's a position, relative position vector. And so the force depends, as distance increases, the force decreases a lot because it's magnitude of r squared. Magnitude of r is just the distance, right? So as the distance increases, the force drops by 1 over the square of the distance. And the direction is given by minus r hat because r hat points that way, but we know that gravitational force is attractive, so that's the force we're calculating here. So what is the magnitude of this constant G? It's 6.7 times 10 to the negative 11. And let's see what the units have to be. This has to come out to newtons. And this is kilogram squared here, and we have meter squared here. So this units of this Newton meter squared per kilogram squared. This is not a number you have to memorize. If you need it, we'll tell you what it is. But it's interesting that it's kind of a small constant. So, questions about this. We're going to spend today working with this. Yes?
So the net force on the system is the force of the object on the system?
So in this particular case, so that's a good question. The question is the net force on the system the force due to this object in the surroundings? Yes, we've defined a very simple situation here where our system is the thing of interest. It could be a moon or something, or a spacecraft. And we've defined a very simple situation where there's only one massive object in the surroundings that's big enough to exert a force that we care about. So in this situation, this gravitational force, which we can calculate that way, would indeed be our net force on the system. And what do you think would happen if there were two objects in the surroundings, though? That's a really good question. So suppose here's our system, but in addition to object 2, we've got an object 3 in the surroundings. So that's a really important question, because rarely in the world is there just one object in the surroundings. And the answer is, fortunately for us, it turns out to be really, really simple. It could have been really complicated, but it's really simple. The net, so object 2 exerts a gravitational force on object 1, so we would calculate it with R12, and we'd get this gravitational force on 1 by 2. And while we're calculating this, we just completely ignore this other object, because its presence doesn't change this interaction. Now, life would have been very much more complicated if it did, but fortunately for us, it doesn't. So then, we say, okay, now let's pretend 3 is the only thing in the surroundings, and we do it again. So this is R13. We go through that whole calculation. We get a force on 1 by 3. And then our net force would just be the sum of the vector sum of those two forces, right? So F net and graphically it would look something like this. Here's on 1 by and here's F on 1 by 2. Here I'll be consistent. And to add them, we're going to move this vector here and draw this sum. So that's a great question, and this is actually has a name. It's called the Superposition Principle. And it says two things. It says, one, the net force on an object is just the sum of the vector sum of the forces exerted by all the objects in the surroundings. It's particularly clear what they are usually in the case of gravitational forces. So F net is just the sum of F sub I from objects in the surroundings. And there's another piece to this that's very important, which is, and the presence of one object in the surroundings doesn't change the force exerted by another object. Now, do these two objects interact with each other? Sure, but we're not interested in that right now. We're just interested in what's happening to this guy.
So 2 and 3 don't affect the attraction for 1.
Yeah, so interestingly, I mean, you can see how complicated it would be if the fact that this number 3 showed up weakened this attraction or something like this. That would make life very, very complicated. So it's really lucky that it doesn't. So it's a very simple situation. We can just calculate all the forces individually, pretending that these are the only 2 objects in the universe, and then add them up, and it works really well. So let's see if we can use this equation just to reason a little bit about gravitational forces before we actually calculation mode. So suppose that we have a planet, it's got some moons. When the moon is at a particular location relative to the planet, the magnitude of the gravitational force is 3 times 10 to the 23rd newtons. What would it be if the mass of the moon were twice as large? So this is a kind of Gravitational reasoning using this equation. How do we do this? Talk to your neighbor.
What they're essentially saying is
Okay, so what's your answer? 1, 2, 3, 4, 5. We've got 4s, we've got 1, we've got 2s. I think we have mostly 4s. So 4 is correct. Let's see why. So the magnitude of this force is equal to the magnitude of minus g m1 m2 over r squared r hat. The magnitude of r hat is 1. So basically we've got g m1 m2 over the distance squared. And so in some particular situation, this is equal to 3 times 10 to the 23rd newtons. So what are we changing in this equation if we triple the mass of the moon? One of these m's, right? M1. So what we're looking at is this. g times a 3m1 times m2 over the magnitude of r squared, right? Because now we multiplied the mass of the moon by the... Everything else stayed the same. Mass of the planet didn't change, distance didn't change, constant didn't change, right? So we change one thing in an equation that looks like we've got 9 times 10 to the 23rd newtons. Questions about that? So we're going to end up doing a fair amount of this, which is reasoning, using an equation to guide proportional reasoning without having to know all the values in the equation. So that's the name of the game. Okay, here's a different situation. So we have the same initial situation. We have the same planet, the same moon. But now we keep the mass of the moon the same, but we move the moon twice as far away from the planet. So we've doubled the distance between the moon and the planet. So what happens? Talk to your neighbor. Okay? What's the answer? Ooh, you guys are pretty good. Okay, mostly 4. That is the right answer. Let's see why. We have G is the same, M1 is the same, M2 is the same, but here the quantity is 2 times the magnitude of R squared, isn't it? And so that gives us a 1/4 times G M1 M2 over magnitude of R squared. And so we would get 3/4 times 10 to the 23rd newtons, or 0.75 times 10 to the 23rd newtons. So well done. Good job. Questions? Okay, so this equation, so we're going to use equations this way too, where it's not just a matter of plugging numbers in and getting an answer, but looking at what the form of the equation tells us about what's going to happen when things change. So 1 over distance squared means double the distance, 1/4 of the force. Direct proportionality to mass means double the mass, twice the force. Okay, so that kind of reasoning from these equations. So there's a lot of information in these equations. Okay, one warm up here. We want to find the gravitational force on the planet by the star. So what's the direction of r hat? Okay, what's the answer? Okay, we've got 2s and 6s, which are the opposites of each other. So they can't both be right. So what's the definition of the object in the surroundings, and it goes to our system? If we're trying to find the force on the planet, what's our system? The planet. So the vector r has to start at the star and go to the planet, right? Therefore, r hat is in same direction, isn't it? So r hat. But so how do we get a gravitational force going that way? It's the negative sign, isn't it? It's the negative sign in that equation that makes the force come out in the right direction. What would happen if we wanted to calculate the force on the star by the planet? We've just changed our definition of system and surroundings, haven't we? Now the system is the star, the surroundings are the planet. In that case, we'd have to draw r the other way, and r hat would be the other way. Okay, let's put it all together and actually do a calculation. So here's a star whose position isn't going to change very much in the next century. And a planet. And we're going to calculate, so the goal, we're going to step through the calculation, but the goal is to calculate the force on the planet by the star. And the reason we want to do that is we want to see what's going to happen to the planet's momentum in the next time interval. So let's take a moment and calculate the vector that points from the star to the planet. This is one where you actually can draw a diagram because we're only in the xy plane, so it's not a bad idea to do a diagram. The good thing about a diagram is that then you can, when you get a numerical answer, you can just look at the diagram and see if it makes sense or not. So let's draw a diagram. They're both in the same quadrant. So we have the planet is 2, 1.5, and the star is, let's make this bigger. So 2, 1.5, and the star is at 1/2. Okay, so what's the answer? Yeah. What's
3.
Oh. Okay. So I'm seeing 2s, I'm seeing 3s, I'm seeing, I don't know, seeing, okay, good. Some people are answering. So it's either 2 or 3. So let's do it. We have, we want the planet minus the star, right? Because that's a vector that starts on the star and goes to the planet. That's the position of the planet relative to the star. So that's going to be 2 times 10 to the 11th, 1.5 times 10 to the 11th, 0 meters minus 0.5 times 10 to the 11th, 1 times 10 to the 11th, 0 meters, which indeed gives us a plus 1.5, a plus 0.50, the 11th, let's get those in there. So that's 2, and let's just confirm it. That says that the vector has, this vector r has a positive x component and a positive y component. And if we start at the star and go to the planet, indeed we're going in the plus x direction and the plus y direction. So that's what our diagram's good for, is making sure that our answers make sense. Okay, questions? Now, it actually is important to get this correct, because if you get the vector in the wrong direction, you're going to get the force acting in the wrong direction, and the planet is going to be repelled by the star. And so your calculations will be doing something that's maybe interesting, but is not the way we think the physical world actually works. So actually, this isn't a nit. This is actually important. You've got to get the signs right. Okay. So what's the distance between the star and the planet? This you have to calculate. There's really no way to do it except just calculate it. Some people have realized that GlowScript will do this for you. Let me point out that even if you don't have a laptop, you can check one out to bring to class if you want to from, there's a place in GAB, I think one of the libraries does it, or actually a Chromebook, which you could get for 150 bucks. We'll do everything we need to do with this class, so. All right, so we need a number. We got a number? Okay, people are saying 3 who've actually done the calculation, and that's right. So the magnitude of r is equal to 1.58 times 10 to the 11 meters. That's 1.5 times 10 to the 11th squared plus 0.5 times 10 to the 11th squared, take the square root, okay. And so what's the unit vector r hat? We need r hat. So speedy calculator, folks. What's r hat? 1. Okay. So r hat is 0.949, 0.316, 0. What are the units of r hat? Right, it doesn't have any, does it? No units.
Just scalar.
What?
Just scalar.
It's not a scalar, it's just a unitless vector. It's because we're dividing, remember r hat is the vector r over the magnitude of r. This has units of meters, that has units of meters. They cancel. R hat is just a unitless vector floating in space, unattached to anything. Unit vectors are interesting. Very useful, though. Okay. So how can you rule out? There's a couple of these you can rule out by inspection, right? So why can you rule out 4? It's just in the wrong direction, isn't it? Why can you rule out 5? It's not a unit vector. Its magnitude is greater than 1. So then the rest you have to actually calculate. Okay, so let's get the magnitude of the force. So what's the magnitude of the force? So I urge you to bring a device for doing calculations to class, because actually practicing this is a good thing. It could be a calculator, it could be a laptop. Okay, who's got a number? Okay, so people are saying it's answer 3, which is 1.34 times 10 to the 22 newtons. Now actually just by estimating we could have eliminated several alternatives, right? Because in the numerator we've got 10 to the 30th kilograms, and we've got 10 to the 24th kilograms, so that's something like 10 to the 54th kilograms squared in the numerator, and we have 10 to the 11th squared in the denominator, which gives us something like 10 to the 22. So subtracting those, we're going to get something on the order of 33, right? 22. Yeah. So we're roughly in the same, right, in the ballpark. But and then we have G, which is 10 to the minus 11th. So we've got a 32 and 10 to the minus 11th. So we could actually, you didn't really have to, with a multiple choice question, you could have estimated it just from the orders of magnitude, right? However, that's the answer. So let's put it together. What's the force? Gonna So what's the calculation we're doing? We're just multiplying the magnitude by minus r hat, right? So we've got a f times minus r hat. So which answer is correct? Yep. Yeah, it's 5. So it's a minus 1.27 times 10 to the 22 minus 4.24 times 10 to the 21, 0 newtons. So this is the force on the planet by the star. Is it in the right direction, given our diagram? Is its direction correct? So it's got a negative x component, negative y component. That means that it's going to be pointing that way, which is correct, because the planet's attracted to the star. The negative r hat. Right. Yes?
Why is r hat negative? Like, how do we put the negative?
Well, because otherwise we get, so it's up there in our force equation, right? So here's our force equation. The magnitude of the force is going to be a positive number. So the magnitude of that whole thing is just going to be g times m1 times m2 over the magnitude of r squared, right? So the pieces that are missing to give us the correct vector equation are the minus sign and the r hat. And remember, we had to put the minus sign in because r hat's pointing the opposite direction to the force. And the reason we have defined r this way, it may seem a little arcane, is that this ends up being exactly the way we're going to need to define it next semester when we talk about electric fields. So we're just going to be consistent throughout this whole thing. So what would, suppose we were calculating the force that on the star due to the planet, what would change? It's just the direction, isn't it? Yeah, it's just the direction. All that happens is the direction of r hat flips, and but that says that the force by the star is a lot bigger than the planet. But the planet exerts the same force on the star as the star exerts on the planet, even though the planet's smaller. So how does it do that? How does it do that? Well, let's think of it. Let's go back to let's make a small particle that's a cluster of 4 atoms, and it's interacting with 1 atom gravitationally. Now what we just said is that the force this big cluster of 4 atoms exerts on 1 atom is equal in magnitude to the force this puny little 1 atom exerts on these 4 atoms. Now, how does that work? Well, let's break it down. So So we'll call these atoms 1, 2, 3, and 4. So atom 1 exerts a force on our system here. And atom 2 also exerts a force on this system. And atom 3 exerts a force on this system. And atom 4 exerts a force on this system. And since they're very close to the same location, the forces are pretty much going to be equal. And so the net force here is F1 plus F2 plus F3 plus F4. And so if we do it graphically, it would be 1, 2, 3, 4. So here's our okay, so each of these atoms exerted a force on our system, the same force, and we added it up and got the net force. Now let's look at what's happening over here. So this guy, maybe we'll call him 5. Number 5 exerts a force on 1. And it exerts the same force on 2. And it exerts the same force on 3. And it exerts the same force on 4. And the presence of these other atoms didn't change these individual force pairs. That's our piece of the superposition principle that really has teeth in it. And even though this atom is in front of that atom, it didn't matter. So we got F net is F5 plus and so we get 1, 2, 3, 4. We get a force that's equal and opposite. Now, so these forces, so this is called reciprocity. And it says that when we're talking about gravitational forces, and we'll see it's true of electric forces also, the force that object A exerts on B is going to be equal in magnitude and opposite in direction to the force that B exerts on A. So that means that when your car collides with a mosquito, which gets squished against your windshield, the mosquito exerted a force of exactly the same magnitude on your car as your car exerted on the mosquito. They had quite different effects, however. So how much did the force by the mosquito change the car's momentum? Not a lot. How much did the force by the car change the mosquito's momentum? Quite a lot, because the mosquito's momentum was a lot smaller and it was a lot easier to change. So the force is going to be equal, but the effect, well, wait a minute. Let's think about that for a minute. If the forces were equal and the interaction time was equal, wouldn't the change of momentum have been the same? So what did change? Velocity changes were different, weren't they? Because the momentum of the car, the change in momentum of the car was exactly the same as the change in momentum of the mosquito, but the car is very massive. And because of that, its velocity didn't change very much, whereas the mosquito's velocity changed a lot. So that same delta P was caused by the same F net, but the effect is very different just due to the very different masses of these two objects. So for the same delta P, change in mass times velocity, if we have a big mass, a small change in velocity, a small mass, a big change in velocity is. So it is possible for these forces to be equal and opposite, but to have, and to make the momentum change the same, but to have a really different effect on velocity. Okay. Questions about gravitational forces now? Yep, okay. So let's put reciprocity here as a thing. By the way, there are some forces where this principle of reciprocity doesn't actually work. It doesn't hold. So it's true for electric forces, it's true for gravitational forces. We'll see that it's actually not true for magnetic forces. So that it's not this allgemeine general thing, it's a particular property of these particular forces. And in general of forces that act along the line between objects. Okay. So we have superposition and reciprocity. Let's get this up here so we can use this board. So we now have a very general way of calculating gravitational forces. Would be convenient to be about 6 inches taller, but however, earlier we talked about a different calculation of gravitational force. We had this thing m times a little g. That was a gravitational force on something near the surface of the Earth, right? Well, why do we have two equations for gravitational force? Physicists read simple descriptions of the world. We should have only one equation for gravitational force. So the question is, where on Earth does that thing come from? And it's actually pretty straightforward. So let's calculate the force on an object that's on the surface of the Earth or near the surface of the Earth using our general equation. We're going to talk about magnitude here. We know what the direction is going to be. So here's the Earth. Here's an object on the surface of the Earth. So we're just going to use this equation to calculate the force on this object. And we're going to be a little bit general and just say it's an object of mass little m. Now, what's the distance between this object and the Earth that we're going to use in this equation. It is the distance to the center. And why is it that? So this is our vector r, but there's a lot of the Earth that's not at the center. It turns out mathematically that and you can actually show this using ordinary calculus. It's just sort of annoying, but if you have a hollow sphere of uniform density, that the force on an object outside the sphere is the same as if Superman came along and crushed this hollow sphere into a point. And you can kind of see how this works, because if we just take little pieces of the sphere and talk about a little piece of the sphere, this little piece of the sphere is pretty close to our object, so it's going to exert a big force. And there are a few other pieces of the sphere that are close to the object, and they're going to exert a big force. But there are a lot more pieces of the sphere that are far away, and so a piece down here is going to exert a much smaller force. And if we add them all up, the fact that our force the force falls off like 1 over r squared, but the amount of material is increasing with radius, with r squared, it turns out that it works out mathematically to look exactly the same as if Superman came and squashed the sphere to a point. And if we think of the Earth as, we can just model it as a series of nested hollow spheres of uniform density. Any one of these hollow spheres is going to act as if it was a point at the center. And so we add up the effect of the entire Earth, and it looks as the same as if it was squashed into a point at its center. So that's the distance that we actually need. So let's figure out what this is going to be. So the gravitational force is going to be capital G times the mass of our object times the mass of the Earth over, what is this distance? The radius of the Earth, right? So that's a constant, the radius of the Earth squared. And so it's going to be equal to, if we bring this little m out in front, it's going to be equal to G times the mass of the Earth times the radius of the Earth squared. And that's 7 times 10 to the negative 11 Newton meter squared per kilogram squared times the mass of the Earth, which I should get right here, which is about 6 times 10 to the 24 kilograms. And the radius of the Earth is on the order of 6.4 times 10 to the 8th, I think, meters. 10 to the 6th. And so if we work that all out, we get this force is going to be equal to the mass of whatever our object was times 9.8 newtons per So this whole thing is the thing we call little g. So why is this a good approximation, though? I mean, what if you're at the fourth floor of a building? You're not on the surface of the Earth. Charles?
The order of magnitude is so high, even a few kilometers won't make a difference.
Yeah, so the radius of the Earth is really big. So if we have 6.4 times 10 to the 6th meters here, even if we went up a kilometer, 10 to the 3rd meters, we're still not very far away. So it's a reasonable approximation, but it is an approximation. And there's another approximation that feeds into this, which was we are treating the Earth as if it was completely, if all these spheres had completely uniform density. So the interior of the Earth is probably the densest, right? It's sort of molten iron, basically. And that's okay. But the Earth's crust is certainly not of uniform density. We have mineral deposits and other things. So there's a lot of assumptions and approximations that go into this. Nonetheless, it's a pretty useful and effective way of doing it. Okay. Okay. So if the Mars rover measured the value of g on Mars by dropping something, say, would he get a value of g that's bigger than 9.8, less than 9.8, or equal to 9.8 newtons per kilogram? Not completely obvious, is it, because of that r squared? So what do you think? Okay, it's not equal. It's either greater or less.
What?
So what did you guys actually work it out? You calculated it? So we want to look at this equation, right? G doesn't change. The mass got smaller. That would decrease the value of g. The radius got a little bit smaller too, right? And so we're squaring a slightly smaller number. So we're dividing by a slightly smaller number. So I could make it a little bigger. And it's just, what'd you get?
Almost there.
You work it out?
Almost.
3.7? Did other people get 3.7?
Yeah.
No? Okay, we'll say 3.7. You really need to work it out. Okay, one final. This one's easier. Maybe? Okay, never mind. This one actually is easier. So you get a half, right? Okay, questions? Yes. Okay, we'll practice. Do you have a question?
No.
You're just thinking about it. Okay, we'll practice gravitational things in recitation. We have a quiz. Calculation device. Oh no, we have a quiz every Thursday. You will want a calculator.